Welcome to G Fun Facts Online, where we dive deep into the most amazing corners of science and technology. Today, we're plunging into the underwater world, but not just to admire the marine life. We're exploring how these incredible creatures are inspiring a revolution in robotics. For centuries, humanity has looked to nature for bright ideas, and the realm of underwater robots is no different. Imagine machines that swim like fish, glide like rays, or even jet like squid, all thanks to millions of years of evolution. This exciting field is called bio-inspired hydrodynamics, and it's changing everything we thought we knew about underwater exploration. So what's the core idea here? It's all about mimicking the ingenious ways marine animals move, sense their surroundings, and even how their bodies are built. Scientists and engineers are studying fish, rays, jellyfish, squid, and countless other aquatic masters to develop robots that can navigate the challenging, unpredictable underwater world far more effectively. This isn't your grandpa's clunky, propeller-driven submarine. We're talking about a new generation of robots designed for agility, efficiency, and adaptability, especially in tight spots where propellers just can't cut it. Nature's swim team is incredibly diverse, offering a goldmine of inspiration. Take fish, for instance. Some undulate like eels, while others, like tuna, use powerful tail thrusts. Engineers have meticulously reverse-engineered the tuna's physique and swimming style to create the robo-tuna, a robot that boasts remarkable speed and maneuverability. Then there's the bioswimmer, also resembling a tuna, designed for tricky tasks like port security and checking underwater structures, especially in choppy or confined waters. It's all thanks to its biologically inspired design, and it's not just fish. Manta rays, with their majestic, undulating pectoral fins, are super-efficient swimmers with incredible agility. Roboticists are trying to replicate this by using flexible materials for fins that can flap and twist, just like the real thing. Think about jellyfish, pulsing their way through the water. Researchers at the Max Planck Institute are developing jellyfish-like robots that could one day gently clean up delicate ecosystems like coral reefs without causing any harm. And what about cephalopods? Squid use a super-efficient jet propulsion system, a concept engineers are keenly exploring. Octopus-inspired robots, with their soft, flexible arms, are being developed for tasks that need careful manipulation and movement in complex, uneven terrains. Some designs are even aiming for adaptive morphology, meaning a single robot could switch swimming styles, say from fish-like to octopus-like, depending on the job. But why go to all this trouble to copy nature? The advantages are huge. Marine animals are masters of energy efficiency, getting the most thrust and maneuverability for the least effort. By copying these strategies, bio-inspired robots can achieve enhanced energy efficiency. Think undulating fins or tails. They can be much more economical than propellers, especially at slow speeds or in tight spaces. This means longer missions and less downtime for recharging. Fish even create tiny whirlpools or vortices with their tails to help them move, and robots can learn this trick too. Then there's superior maneuverability and agility. The flexible bodies and fins found in nature allow for lightning-fast turns and pinpoint precision, which is absolutely critical for navigating tricky underwater landscapes like coral reefs, shipwrecks, or around submerged pipes. And how about stealth? Mimicking the look and movement of marine life can make these robots much less noticeable. This is a game-changer for wildlife monitoring or even military surveillance. The gentle, undulating movements of fin-based robots also create less noise and a weaker hydrodynamic wake compared to noisy propellers, minimizing disturbance to sensitive marine environments. Plus, these designs are often more adaptable and stable in varying water conditions because their propulsors are inherently flexible. It's not just about movement, though. Bio-inspiration extends to how these robots sense and control themselves. Marine animals have incredibly sophisticated senses for navigating, finding food, and avoiding danger in murky or pitch-black waters. Researchers are developing artificial lateral lines, inspired by the flow-sensing organs in fish, and biosonar to give robots super perception. Imagine robots gathering environmental data with unprecedented accuracy. They're also working on integrating sensing and propulsion. Many fish have sensory receptors in their fins, allowing for a closed-loop system for incredibly fine-tuned control. Replicating this is a major research goal. And get this, scientists are even drawing inspiration from the collective behavior of fish schools to develop control algorithms for swarms of robots, perfect for tasks like large area surveys. To truly bring these bio-inspired designs to life, the right materials are key. We're talking about soft robotics and advanced materials. To mimic the amazing deformability and adaptability of marine organisms, robots need materials that can bend, twist, and change shape. Soft robotics, using materials like silicone, is playing a massive role. These soft-bodied robots are more adaptable and can interact more safely with delicate marine life. Then there are smart materials, like shape memory alloys, or special composites that change shape in response to electricity or heat. These can act like artificial muscles. And how do they build these complex designs? Additive manufacturing, or 3D printing, is essential. We're even seeing research into 4D printing, producing machines that can literally morph and adapt to different environments on their own. Of course, this incredible journey isn't without its challenges. Replicating the intricate mechanics and control systems perfected by Mother Nature over millions of years, that's incredibly complex. Developing control algorithms for these super flexible robots is a huge hurdle. Finding materials that are both flexible enough for lifelike movement and tough enough to survive the harsh underwater world, think pressure, salt water, and things growing on them, is another big one. Powering these untethered robots for long missions and giving them smart, autonomous decision-making capabilities are also ongoing quests. And then there's the challenge of seamlessly integrating all these systems, propulsion, sensing, control, and power, into one compact, efficient package, not to mention making them affordable to produce at scale. Despite these hurdles, the future is incredibly fluid and exciting. The applications for these bio-inspired underwater robots are almost limitless. They're perfect for environmental monitoring, studying fragile coral reefs, mapping marine habitats, collecting water samples, and monitoring pollution with minimal disturbance. Imagine them exploring underwater caves or ancient shipwrecks. For oceanography, they can help us explore the deep sea, still largely uncharted territory. Soft robots inspired by deep-sea creatures could offer new ways to handle extreme pressures. They can inspect underwater pipelines, cables, offshore platforms, and ship hulls, performing maintenance tasks too dangerous for human divers. In search and rescue operations, their maneuverability could be life-saving. For military and security, think stealthy surveillance. The Ghost Swimmer drone is a real-world example. They could even help in aquaculture, monitoring fish stocks, or assist archaeologists in gently recovering submerged artifacts. The field of bio-inspired hydrodynamics is moving fast. It's a collaborative dance between biologists, engineers, material scientists, and computer scientists. We can expect even more mind-blowing advancements in novel designs, AI-driven control, new smart materials, enhanced senses, and even cooperative swarms of robots. As we continue to unlock the secrets of aquatic life, our underwater robotic explorers will become even more capable, opening up entirely new ways to understand and interact with the vast, mysterious underwater world. The silent, efficient swimmers of our oceans aren't just a source of wonder. They are a direct blueprint for the future of underwater technology. That's all the time we have for today on G Fun Facts Online. We hope you enjoyed this deep dive into the future of underwater robotics. Join us next time for more fascinating facts from the world around us. Thanks for listening.